internal combustion engine fundamentals we were discussing. We were discussed that purpose of an engine is to convert heat into work. Then this conversion efficiency also we have defined in terms of thermal efficiency, and we said never we are achieving 100% conversion of heat into work. Same time we have discussed that for converting heat into work, engine has to be operated in a cycle. Cycle may consist 4 strokes, cycle may consist 2 strokes. In 4-stroke engine, when 4 strokes are completed, crankshaft is getting rotated by 2 revolutions. Whereas in the case of 2-stroke engine, when 2 strokes are completed, crankshaft is rotated by 1 revolution. Then we have defined thermal efficiency, conversion efficiency, and we have observed that conversion of heat into work is very less, around say 30% conversion of heat into work we have observed. Roughly 1/3 heat is going waste in cooling water, roughly 1/3 is going in exhaust gases, and then some heat transfer losses, friction losses in a cycle. So always our efforts are to increase this efficiency. Same time we have said that from a given size of engine, we want that output of engine should be maximum possible, and that we have defined in terms of power to weight ratio. Always we want to achieve higher power to weight ratio, means power from a given size of engine should be more, weight of the engine should be less. Then second we said conversion efficiency, thermal efficiency of the engine should be as high as possible. Third we said exhaust emissions, that is carbon monoxide, oxides of nitrogen, unburnt hydrocarbons, smoke, that should be minimum possible. And fourth one, we said engine operation should be very smooth, running of the engine should be very smooth. Today we will be discussing some of the terminologies of an engine, and same time, because various types of fuel we are using even in 4-stroke engine, fuel may be diesel, fuel may be petrol, fuel may be any gaseous fuel just like natural gas, LPG. So depending upon the fuel, what changes in the performance is coming, and what are the design changes in an engine. Suppose one engine we are using for the diesel fuel, another one we are using for petrol fuel. What changes are there? What differences are there? So one by one we will be discussing some of the differences, and finally we will be concluding this whole lecture. One small video I will be showing you the functioning of the 4-stroke engine, just to review the processes in 4-stroke engine which are taking place. Just you will observe that how 4 strokes are completed, how opening and closing of the valves. Yes, you can observe there are 4 cylinders, 4 pistons are moving simultaneously. Where color is becoming red means combustion is taking place, blue is compression and expansion, the reddish is the blackish color which is there, that is after combustion, it is expansion and this exhaust stroke. So 4 strokes are indicated. You can see here crankshaft. With crankshaft, with the help of connecting rod, all 4 pistons are connected, and all 4 pistons are moving simultaneously. All are connected with a common crankshaft. Over these pistons, another part which we are having, that is camshaft, and camshaft is connected with different valves. In one cylinder there is 2 valves, one is for the purpose of taking fresh mixture. Here in this case 2 inlet valves are there and 2 exhaust valves are there. You can see outlet valves are also 2. Here in this case, for the purpose of start of combustion, we are having a spark plug. Yes, combustion has taken place. This is compression. Yes, compression stroke is going on. Compression stroke is going on. When air fuel mixture is compressed, that time spark plug will be initiating spark. It will be giving intense energy. This red color you can observe, it is start of combustion. Yes, combustion flame is moving, combustion is completed, piston has reached to bottom dead center, power stroke has completed. Now burnt products are going out. Exhaust valve is open and burnt products are going out. This is exhaust stroke. Our efforts are that combustion should be complete, means whatever mixture we have taken into the cylinder, complete combustion of that mixture, and same time the burnt product should go out. So intake, it is fresh mixture coming in, compression, the mixture is compressed, then combustion is taking place, and finally burnt products are going out. The power which we are getting on the crankshaft, it is continuous, yes. In one cylinder there is power stroke, another one is compression, third one may be in exhaust, like this one, so power is continuous. From every angle you can see. So this is regarding the working of 4-stroke engine. Both type of engines we are when we are discussing, one is spark ignition engine, another one is compression ignition engine. Two engines, two cylinders are shown in this slide. First one, spark ignition engine, where the fuel which you are using, generally it is petrol. So sometimes these engines are termed as petrol engine, sometimes we are saying spark ignition engines. In this case, fresh mixture, air and fuel vapors are being sucked into the cylinder, and same is compressed, and after compression spark is initiated. The ignition temperature of petrol is around 450 degrees Celsius. So certainly starting the combustion, the temperature of the spark should be much higher than 450 degrees Celsius. Then only combustion can be initiated. So the voltage which you are initiating with the help of spark plug, it's very high, around 100,000 volts of electricity we are producing here. With the help of a battery, normally the battery which you are using in engines, it is 12-volt battery. That voltage is being enhanced, it is being stepped up, and up to a very high voltage it is set up with the help of ignition coil. Separately we will be discussing ignition coil, but at spark plug electrodes, the voltage which you are receiving, it is around 100,000 volts, 1 lakh volts we are receiving here. So in the case of spark ignition engine, after compression, temperature is around 350 400 degrees Celsius, pressure is around 10 bar of the mixture, and in that mixture we are initiating the spark. The compression, the view of the piston which is here shown here, it is roughly at its top dead center, and inside the cylinder, if you are measuring the pressure before start of combustion, before start of spark, pressure is around 10 bar. Whereas another side, I am showing another type of engine, that is compression ignition engine. In this case, only air is taken first in suction stroke and the air is compressed. In the case of spark ignition engine, air plus petrol vapors, both we have taken inside the cylinder. For mixing air and petrol vapors, we are using carburetor there. In the case of diesel engine, in suction only air we are taking. And after completion of compression, here compression is very high. Compression ratio is significantly higher. In the case of petrol engine, compression ratio starts from say 8.5, even it can reach up to 15. But in the case of diesel engine, it starts from 15 itself. So starting lowest compression ratio normally which we are getting in the engine, it is around 15. But maximum compression ratios these days in some of the vehicles, it is even 25. So here compression ratios are quite high. Higher compression ratio means after compression, during compression stroke, when piston will be reaching to TDC, the clearance volume will be very small. That's why compression ratio is higher. Compression ratio is our swept volume, means volume between TDC and BDC, and then volume, clearance volume, that is after TDC the volume which we are having. So compression ratio is swept volume plus clearance volume divided by clearance volume. So clearance volume is dividing factor. It means smaller the clearance volume, higher the compression ratio. In the case of diesel engine, this compression ratio value is quite high as compared to spark ignition engines. So when compression ratio in diesel engine is higher, and if compression ratio is higher, means pressure after compression will be higher. Normally in the case of diesel engine, pressure after compression can reach up to 40 bar. I said in the case of spark ignition engine, this pressure after compression is around 10 bar, here it is 40 bar. If it is 40 bar, then certainly temperature of air is significantly higher, and we are keeping higher compression ratio so that even without the use of spark plug, the combustion of diesel can be initiated. Here with the help of injector, high pressure sprays is entering into the cylinder of diesel. Diesel is injected into the cylinder. The sprays may be 3, it may be 5, in some of the cases even 7. In some special engines even single spray is also used, and pressure of this fuel is very high. It can be more than 1000 bar. Very high pressure of this fuel, and droplet size is also very small, because size of the holes which are in this nozzle, the size is very small, say around 0.2 mm, very small holes which are even not visible with naked eyes. So through these holes high pressure diesel is injected into the cylinder. The control of speed of the piston, in the case of spark ignition engine, the amount of air plus fuel which is entering into the cylinder, with the help of a throttle valve we are controlling. In case of petrol engine, in case of spark ignition engine, we are using carburetor for mixing air fuel mixture, as well as its quantity of air fuel mixture which is entering into the cylinder. It is controlled with the help of a valve. It is with the help of a throttle valve which is available in the carburetor. So amount of mixture which is entering into the cylinder, it decides the speed of the piston. According to the load or according to the speed requirement from the engine, quantity of air fuel mixture is varied. So these type of engines, the spark ignition engines, are quantity governed. Means quantity is controlled by driver by varying the position of throttle. But ratio of air and fuel, in the case of spark ignition engine, it is more or less constant. It is around 15, that is termed as chemically correct air fuel ratio or stoichiometric in some of the cases. So meaning of chemically correct air fuel mixture is that for combustion of 1 kg of petrol, the air requirement is sufficient and combustion will be complete. The combustion products will be having carbon dioxide, it will be having water vapors, it will be having nitrogens, it won't be having any CO in exhaust. Means combustion is complete. For making combustion complete, 1 kg of petrol should have mixed with 15 kg of air. It is a thumb rule. It is a chemically correct mixture. But for controlling the speed, we are keeping this air fuel mixture constant, but amount of mixture which is entering into the cylinder, that we are controlling. Means quantity of this air fuel mixture we are controlling. That's why these engines are termed as quantity governed engines. In the case of diesel engines, there is no throttle valve, there is no control over the amount of air which is entering into the cylinder. The quantity of air, whatever the speed of engine may be, whatever the load on the engine may be, the quantity of air which is entering during suction stroke, it is always constant. Only for changing the speed of the piston, increasing the speed of the piston, we are increasing the quantity of diesel which is spread into the cylinder in a cycle. So amount of air is constant, amount of fuel is varying, means quality of mixture which is burning into the cylinder, the quality of mixture is changing. Depending upon the load, depending upon the speed, quality of mixture is changing. It may start from 20 to somewhere around 80. 20 means full load. When engine is fully loaded, that time air fuel ratio is 20. 20 when I am saying air fuel ratio means 20 kg air, 1 kg fuel. When I am saying 80, 80 means 80 kg air, 1 kg fuel. Very lean mixture. Very lean mixture. When 80 ratio 1 we are having, and it is idling condition, when there is no load, just we are waiting on a red light, just engine is in start condition, and amount of fuel which is injecting which is injected into the cylinder, that amount is very small. That situation is termed as idling situation. The fuel which is supplied to the cylinder, it is just keeping piston in moving condition, the crankshaft is in moving condition, but no power is transferred on the wheels, it is just standing. So in idling, air fuel ratio in diesel may be 80, at full load it may be 20, whereas in the case of petrol engine, this air fuel ratio is always constant 15. So petrol engines are constant air fuel ratio operation engines, whereas in the case of diesel engine, the air fuel ratio according to the requirement of an engine, it is varying. Diesel engines are quantity governed engines, whereas the petrol engines are quantity governed engines, whereas diesel engines are quality governed engines. Just some terminology I am explaining here. The diameter of the cylinder, which is termed as bow, I am indicating with D, it is diameter of the cylinder. It is indicated in millimeters, diameter of the cylinder in millimeter. Then Vs, which is shown, it is volume between TDC and BDC in the cylinder. It is termed as swept volume. Above piston, the volume which is there, it is clearance volume, up to which we are compressing the air in the case of diesel engine, air plus fuel mixture in the case of petrol engine. So it is clearance volume. So distance between TDC and BDC is stroke. The diameter or bore is indicated by D, swept volume Vs, and we are indicating the swept volume in terms of cc. Cc stands for centimeter cube. On some of the vehicles it is written, just like Honda motorcycle, it is written 100 cc. 100 cc means swept volume of that cylinder is 100 centimeter cube, and it is calculated pi by 4 into diameter of square into stroke length. So if 100 cc I am saying means pi by 4 into d square into stroke length s is equal to 100 centimeter cube. That's the meaning of 100 cc. So this is swept volume, then clearance volume. If d equal to s, normally if diameter of the cylinder and stroke length is distance covered by piston between TDC and BDC. If d and s is equal, suppose diameter is 100 mm and stroke is also 100 mm, the engine is square engine. When diameter and stroke of the piston is equal, these type of engines are square engine. Whereas in the case of most of the cases, particularly in spark ignition engine, our diameters are lesser than our stroke length. We want that after giving spark, once combustion has been initiated, the flame is propagating, diameter is more means flame has to travel more distance. In the case of petrol engine, we want that flame should travel a minimum distance for smooth combustion to avoid serious abnormality in the combustion. So normally in the case of petrol engine, diameter is kept small and stroke length is kept longer. Whereas in the case of diesel engines, the another type of engine, where d is greater than s, diameter is more, stroke length is less. So in diesel engines, always our efforts are that diameter of cylinder should be larger, the diameter should be more. We want that when we are giving injection, when fuel is injected, no spray should touch to the cylinder walls. That should be a larger distance. If they are touching in liquid form, they should cover longer distances. So in the case of diesel engines, normally diameters are more as compared to stroke, whereas in the case of petrol engine, the diameters are less as compared to stroke. When d is equal to s, it is termed as square engine. When d is less than s, it is under square, normally petrol engines. When d is greater than s, it is over square, normally they are diesel engines. Just compression ratio I am explaining, and compression ratio I said total volume means swept volume plus clearance volume, the total red V1 which is indicated when piston is at BDC, and for an example here total volume V1 is equal to 14 cc, 14 centimeter cube, just example I have taken. So 14 cc total volume is there. After compression, whole mixture will be compressed into the clearance volume. After compression stroke, completion of the compression stroke, total volume, clearance volume which will be having, it is only say 1 cc for example. So total 14 cc volume has been reduced, has been compressed to 1 centimeter cube. Means compression ratio of an engine is total volume which we had 14 centimeter cube, which has been reduced finally equal to clearance volume, that is 1 cc. So 14 divided by 1, it is compression ratio. So compression ratio of this engine will be 14. This compression ratio is very important parameter of an engine. When we are designing engine, the serious checks has to be kept on this compression ratio. In the case of petrol engine, suppose we have increased this compression ratio, it will be creating lot of problems in combustion. In the case of diesel engine, if compression ratio if you have kept low, again combustion will be very difficult. So it is very significant parameter as far as the operation of the engine is concerned, as far as performance of the engine is concerned, even the exhaust emissions are concerned, even power to weight ratio is concerned, or even maximum temperature of the cycle, maximum pressure of the cycle, smooth running of the engine is concerned, this compression ratio is very important. Here I am showing that how compression ratio is affecting our thermal efficiency. X axis is compression ratio, y axis is thermal efficiency, and you can see from here as compression ratio is increasing, thermal efficiency of Otto cycle is increasing. Otto cycle I am saying for petrol engines. So as compression ratio is increasing, efficiency of Otto cycle is increasing. There is a correlation between thermal efficiency and compression ratio. The relation which is indicated here, left hand side I am showing thermal efficiency, another side I am showing compression ratio, and then index of compression gamma also. Index of compression is Cp over Cv. Cp value of the mixture which is compressed, and same time Cv value of the mixture. The Cp is specific heat at constant pressure of the mixture, Cv is specific heat of the mixture at constant volume. So Cp Cv ratio decides gamma, R is compression ratio. For air, value of gamma is 1.4, so constant value of gamma will be taking for air, and we will be assuming here that throughout the cycle value of gamma remains constant, means Cp Cv value remains constant. That assumption we are having while we are analyzing the Otto cycle. And value of compression ratio for a particular ratio which for which engine is designed, that compression ratio value we are putting into this one, and we are calculating thermal efficiency. It can be seen from here that as compression ratio is increasing up to certain limit, value of thermal efficiency is increasing very sharply. After that the curve becomes more or less flat. So after that the change in thermal efficiency is not significant, but it can be seriously it can be seen that when compression ratios are higher, the value of thermal efficiency of an engine is higher. Just one example of diesel engine I am showing you. These diesel engines are having quite high compression ratio. Quite high compression ratio means their thermal efficiencies are higher. That's why I written here efficient diesel engines. As compared to petrol engine, the compression ratio of diesel engines are higher and they are more efficient. When efficient I am saying it is in terms of thermal efficiency. The work output divided by heat supplied, it decides the thermal efficiency. For a given amount of heat, we want power output should be more. So more the power output, more the efficiency. And for same size of engines, if you are comparing, your diesel engines are more efficient as compared to petrol engines because their compression ratios are higher. The value of compression ratios here I am comparing for some petrol engines I am showing you. First one two-wheeler I am showing you here, Royal Enfield. You may be knowing this is manufactured by some British company, Royal Company, and here compression ratio is 8.5. In petrol engine compression ratio is 8.5. In earlier days the value of compression ratios was very low, 4.5, then it became 6, up to last 5 years it was even 7, then 7.5. But now many changes, design changes are there in spark ignition engine. Even the quality of fuel which we are using in terms of octane number, the quality of fuel is good. Higher the octane number means the combustion will be smooth, without any knocking combustion will be. This compression ratio is affecting knocking of the fuel. Knocking means it's auto ignition. When we are having higher compression ratio, chances of auto ignition of petrol will be much more. But these days the quality of the fuel we are improving by adding some additives. I will be discussing in afterward my lectures that quality of fuel can be improved, particularly petrol quality, by adding some additives, and it will be giving higher octane rating, means higher compression ratio, without affecting the combustion or inside the cylinder, without affecting the smooth running of the engine. We can increase the compression ratio. So one example of 8.5 compression ratio. Another side I am showing you Kawasaki Kawasaki, it's Japanese vehicle, again two-wheeler, and in this case even compression ratio is 9.5, very high compression ratio. So these engines as compared to 8.5, when we are having compression ratio 9.5, the combustion of the fuel will be lesser, efficiency will be better, or mileage of the vehicle will be better. Even some of the vehicles today which are termed as high performance engines, Toyota car I am showing you, its compression ratio is 10.5. So in Royal Enfield I was showing you 8.5, Kawasaki 9.5, here in Toyota even it is 10.5, and this is in the category of high performance vehicles. And in these vehicles the specialty is the way fuel is injected into the cylinder. It is not conventional carburetor where air fuel mixture was prepared in the carburetor, then it was being sprayed into the cylinder. In this case air is taken separately and fuel injection system is utilized. The control of fuel during injection, rate of injection, pressure, everything is controlled very precisely by using microprocessors. So these special vehicles, the high performance vehicles, are using fuel injection system. Another vehicle, if you can see from here, it is Aston Martin. Here compression ratio is 11 point, and this 12.5, 11.5, yes, 11.5 compression ratio. Then another car, German car, Porsche, its compression ratio is 12.5. The output of this car is around 400 horsepower. Very large size engine it is having. It is 4-stroke and output is 400 horsepower. Normally the cars which we are using, their output is 50 kilowatt, 35, 40, 45 kilowatts, but here output is 400 horsepower. 400 horsepower, I am saying it is around 300 kilowatt. So very large size engine. The power output from that engine is significantly higher. Then another very important vehicle, high speed vehicle, and which is being used for the purpose of in the case of racing cars, this type of vehicle is used. Here compression ratio is 14. It's Mazda Sky Active. Again fuel injection system is being used. It is one of the best vehicle which is available on the roads, and cost of the vehicle is around $100,000. In Indian terms, if I am saying, around 70 lakhs. This much is the cost of this vehicle. So today the trend is to increase the compression ratio in spark ignition engine. The output from the given size engine will be increasing, and same time efficiencies are increasing. Just specification of this Porsche car I am showing you. Maximum power I said it is around 400. It is exactly, it is 420 horsepower, and engine RPM is 6500. At this particular RPM, this power output is obtained. So petrol engines are also high RPM engines. This value of RPM 6500 we are not achieving in the case of diesel engines. So petrol engines are high RPM engine, and even compression ratios are becoming comparable to diesel engines also. And acceleration, you can see, when acceleration we are defining, then we are saying in what particular seconds the particular speed is achieved. Say here it is said stationary vehicle, initially we are having, it has achieved the speed of 60 miles per hour, and only 4 seconds it has taken. You can imagine how rapid that acceleration is, how rapid movement of the vehicle is, how rapid response of air fuel mixture inside the cylinder is. The better the response, better the combustion, better the power, and higher the acceleration. Even the maximum speed it can be achieved, it is around 190 miles per hour. Fuel consumption on highway and the city, exactly it is not mentioned, it is mentioned in TBD. TBD stands for the testing on bed. Basically the testing which is being done of the vehicle in the laboratories or in the industries, it is on the bed. So on bed, if this test is being done, then it is the mileage is coming, it is inside the industry. On actual road, when it will be moving, that may be something different, slightly it may change. The same conditions we are unable to achieve into the industries, which actually when vehicle is moving on the road, the resistances, the road conditions, the temperatures, pressures of the air, everything which is obstructing the movement of vehicle, those conditions may be different. So theoretically when we are testing on the bed, that time the mileage which we are getting, that can be measured, but it may not be exactly which we are receiving on the road. And cost also you can see here, 110,300, it is 100,000, 110,300. This is the cost in terms of US dollar. The different cars in the form of compression ratios, it has been compared. In the case of petrol engine, first vehicle I am showing you, here compression ratio is varying from 8 to 12. Some of the vehicle, majority of the vehicles which are conventionally moving on the roads, conventional vehicles, conventional petrol engines which we are using, their compression ratios are in the range of 8 to 12. But high performance car, which I just mentioned earlier, normally they are racing cars. In this case, compression ratio is up to 15. This compression ratio is in petrol vehicles where fuel injection system we are using, and 8 to 12 is now, it is very much in use. Even the cost of the conventional vehicles are also not very high. In the case of sports car, this ratio is quite high, and in the case of diesel, which I have shown, third type of vehicle, air compression ratio is 20. So in the case of diesel engines, clearly you can observe there is a significant difference. 8 to 12 we are comparing conventional vehicles of petrol, and diesel it is 20, even more than 20, up to 25 compression ratios are used in the case of diesel vehicles. And these are the specification of this car which I have shown you, Sky Active car, Mazda. Here different models are having different displacement. Displacement is swept volume. Swept volume, in one case it is around 1300 cc, another case around 1500 cc, third case it is 2000 cc roughly, and fourth case is 2500 centimeter cube. As swept volume is increasing, engine output is increasing. So larger the size of the cylinder, it is more the output. And this 2500 or 2000 cc which I am showing you, it is not the one cylinder swept volume. It is all 4 cylinders or 6 cylinders which are being used. Addition, if I am adding all swept volumes of all the cylinders, then it is becoming 2500 or it is becoming 1300. The diameter of the piston, in one case 82 mm, another case 85.8, third case 91.2, fourth case 100 mm. These are the these are the piston strokes, means distance between top dead center and bottom dead center. Cylinder boards diameters are indicated on other side, 71, 74.5, 83.5, 89, and everywhere you can observe as compared to diameter your piston strokes are longer. Means here D is less, here S is more, it is under square. So in petrol engine I conveyed you the diameters are less, stroke length is more, cylinder block is made with alloy aluminum which can sustain significantly higher temperature. It is stronger also in for sustaining high pressures also. Cylinder head, there are two major parts. One is cylinder block, which is capturing all cylinders, connecting rod, this crankshaft, that is in the cylinder block, and another one is cylinder head, which is covering the cylinder block, and it is having all the valves, it is having all the spark plugs into this one, and camshaft which is there, it is for opening and closing of the valve, that is valve train. And DOHC means dual overhead cams. Two cams are there, which is one camshaft is for opening and closing of inlet valves, another camshaft it is overhead, it is above the valves, and it is for the purpose of opening and closing of the inlet valve. So one camshaft is utilized for inlet valves, all the inlet valve of all the cylinders, and another camshaft is used for opening and closing of exhaust valves. This I am showing you pressure variation when piston is moving inside the cylinder, how pressure is varying inside the cylinder. You can observe from here, somewhere I am showing you TDC, another side I am showing you BDC. So TDC, BDC, movement of the piston in suction stroke, if you observe, yes, just you see the intake stroke. In the case of suction stroke, more or less pressure inside the cylinder is atmospheric, slightly lower than atmospheric, low pressure, no variation in the pressure. Piston is going in downward direction, and same time fresh mixture is entering into the cylinder. So more or less pressure is constant. Yes, and somewhere here we have opened the inlet valve, starting of inlet valve opening. When inlet valve starting opening we have started, that time even exhaust stroke was going on. Here I am indicating EVC, it is exhaust valve closing. So inlet valve we have started to open, and same time exhaust products are going out from the previous cycle. So inlet valve is in open position, means starting of opening of it has been started, and still exhaust valve has not been closed. Here we have closed the exhaust valve, and then actual compression started, actual suction has started. The closing of the exhaust valve from here, piston is going down, fresh mixture is coming to the cylinder. Here inlet valve has been closed. So on this axis we are showing pressure. Here it is theta, it is crankshaft rotation. So from inlet valve opening and inlet valve closing, it is slightly before TDC we opened the inlet valve, and closing it is after BDC. Between TDC and BDC, during suction stroke, crankshaft rotation is actually it is 180 degree. But you can observe here that opening of the inlet valve we have started to open it before TDC, and closing we are doing after BDC. Means it is more than 180 degree. Your intake stroke is more than 180 degree, and pressure variation, if you see, more or less constant pressure inside the cylinder. Once your inlet valve has been closed and piston has started to move in compression stroke towards TDC, from BDC to TDC, when it has started to move, the mixture has been compressed and pressure inside the cylinder become significantly higher during compression stroke. So this diagram is pressure versus theta. This diagram we are obtaining while piston is moving inside the cylinder, and we have put one sensor here, pressure pickup we have put in the cylinder head, and that is giving the pressure values. Yes. Then after compression, somewhere combustion will be started. Here combustion duration is also indicated. Once we have started this spark, immediately total fuel won't be burning. It is taking some time. In combustion it is taking some time. So in terms of theta, if I am saying, in terms of theta if you measure, in case of petrol engine this duration may be 40 to 45 degree of the crankshaft rotation. So in theoretical cycle, if you remember, in the case of Otto cycle we said heat addition is at constant volume, means without consuming time heat is being added theoretically we said. But in actual cycle, for the purpose of combustion, some significant time is needed, 40 to 45 degree of the crankshaft rotation. Yes, this is combustion duration, and one of the reason of becoming lower efficiency in the case of engines, that is it is not exactly constant volume combustion. If constant volume combustion is there, then efficiency of cycle will be much more. If it is taking some time for the combustion, the efficiency is going down. So theoretically, if I am saying we need constant volume combustion without giving any time, total heat which has to be supplied in the cycle, it has to be added. But in actual cases it is taking time. After starting the spark, flame is reaching to up to the end portion of the cylinder, it will be taking some time. Then from TDC to BDC, high pressure expansion is taking place here. Again both the valves are in closed position and expansion is taking place. Expansion is up to BDC. But you observe here, before completion of this expansion, we have started to open this exhaust valve. When expansion stroke is going on, before that, before completion of the expansion stroke, we have started to open this exhaust valve, and burnt products have started to go out. Initially pressure is significantly higher when we started to open the exhaust valve. One situation may come when pressure inside the cylinder become more or less atmospheric. That period, till the point where it is becoming atmospheric, this period is termed as blow down period. Opening of the exhaust valve and pressure inside the cylinder, when it is becoming atmospheric, this period is termed as blow down period, and after that burnt products are going out. It is the exhaust stroke. Before completion of the exhaust stroke, before reaching the piston to top dead center, means when this exhaust stroke will be completed, before that we have started to open the inlet valve opening. Yes, inlet valve opening we have started from here, and exhaust valve will be closed. So this cycle will be completed like this one, from here to here. From here to start of suction to end of exhaust, crankshaft will be rotating by 720 degree. Out of 720 degree, roughly 180 degrees for compression, roughly 180 degree for expansion, roughly 180 degree for suction, and 180 degree for exhaust. Out of 720, you can observe here 40 to 45 degree is being given for the purpose of combustion. So on P theta diagram, this combustion, compression, suction, exhaust is indicated, and these pressure traces has been taken with the help of one pressure pickup, which normally we put on the cylinder head in the laboratories, of the industries, in the laboratories of the academic institute. These pressure theta diagrams are analyzed very seriously, and the shape of this P theta diagram decides the engine efficiency, engine output, operation of the engine. So this shape is very important, and always we want the peak pressure which is coming inside the cylinder. Here in this, peak pressure is coming slightly after top dead center. Always we want that peak pressure due to combustion which is coming inside the cylinder. One is compression part, then heat addition part, and it is making pressure inside the cylinder significantly higher. This peak pressure we want it should come after slightly top dead center, 10 to 15 degree after TDC it should come. This peak pressure after combustion in diesel engine it is around 70 bar, 70 to 75 bar. In the case of petrol engines it is around 17-18 bar. So as compared to diesel engine, peak pressures in the cylinders are in the petrol engines are low. In diesel engines it is significantly higher. I am saying after combustion, in the case of diesel engine peak pressure is around 70 bar. In the case of petrol engine it is 15-16 bar. After compression, without combustion, just we are compressing, say compression ratio in petrol engine set 8, roughly after compression pressure we are receiving around 10 bar. In the case of diesel engine where compression ratio is 15, after compression, without combustion, I am saying just air we are compressing, the pressure which we are getting it is around 38-39 bar, 40 bar. The same I am comparing this P theta diagram I am converting in the form of pressure volume diagram. Pressure is same, this axis is same, this axis is same, this theta as crankshaft is rotating, piston is moving inside the cylinder, volume is changing. So this theta we are converting in the form of volume. The geometry of the cylinder piston we have taken here, the movement of the piston, the angle of the connecting rod, the crankshaft rotation. On the basis of that theta, depending upon the length of the connecting rod, the diameter of the crankshaft, on the basis of this one we are calculating the volume of the cylinder by geometrical calculations. And with respect to pressure, how volume is changing here. So change in volume, change in pressure, and PV diagram. This is PV diagram. Just P theta diagram I converted into the form of PV diagram. Here suction stroke it is below atmospheric, the compression stroke, then some heat addition, then power stroke here, opening of the exhaust valve, closing of the exhaust valve somewhere here, opening of the inlet valve somewhere here during the exhaust stroke. So this P theta diagram, PV diagram, in some of the cases for the purpose of analysis of the cycle we are using PV diagram, in some of the cases it is P theta diagram. But advantage of PV diagram is we can calculate the area of this diagram, which will be giving you indicated power. This will be giving you pumping power, negative power in fact, and on the basis of this area equal to some rectangle we are drawing, and that rectangle will be giving you as the indicated mean effective pressure. Here it is pumping mean effective pressure, this negative area. Always we want to decrease this negative area, we want to increase this volume. Larger this volume, more the power of the engine. So always efforts are the area of the PV diagram should be much more. This will be more if compression ratios are higher. If compression ratios are higher, the pressure will be much more, and if pressures are higher, the area of this diagram will be more. So use of this P theta diagram, conversion of this P theta diagram into PV diagram is also very important, and small computer program can be generated which is the converting this P theta diagram into PV diagram while we are analyzing or while we are doing some research. This I am showing you. The upper area which I have shown you, that this yellow lines if you see, the total area which this diagram is having, upper diagram is having, I converted into a small rectangle. Yes, that is having the equal area of this diagram. The area of this rectangle is output from that one particular cycle, engine output in that one cycle, and the number of cycles per minute which we are having, it is RPM of the crankshaft divided by 2. So this height Pm which is there, which is indicated, it is mean effective pressure. This mean effective pressure is very, very important. Higher the mean effective pressure, higher the power output, and theoretically we are assuming that during expansion stroke one constant pressure Pm is working on the piston and which is responsible for giving useful output. This line where pressure variation is continuously taking place during expansion stroke, we have converted into a constant pressure. Yes, constant pressure, by assuming that the total area of this PV diagram we have converted into another PV diagram in the form of a rectangle, and height of this rectangle is mean effective pressure. This calculation of this one we are doing, calculation of this mean effective pressure into swept volume into N divided by 120 is indicated power, where Pm is mean effective pressure, L is stroke length, A is area of the piston top, and N is engine RPM. So, indicated power can be calculated like this one. Another difference which we are observing from here from both auto and diesel, I am comparing here. In the case of auto cycle, the mixture which is entering, the green mixture which is indicated here, it is homogeneous mixture. Homogeneous means outside the cylinder with the help of carburetor, air and petrol has been mixed properly, and then it has been supplied during suction stroke. Whereas in the case of diesel engine, other side you see the mixture is heterogeneous, the charge is heterogeneous. Heterogeneous I am saying because during suction stroke only air has been taken, and somewhere near compression, after compression the diesel is injected. So, the mixture which is available inside the cylinder any time, that is heterogeneous, means air fuel ratio nowhere it will be constant. So, diesel engines are having heterogeneous mixtures because separately diesel and petrol is supplied to the cylinder, whereas in the case of petrol engine homogeneous mixture we are supplying. In the case of diesel engine separately air and diesel is supplied, so mixture always remains heterogeneous here. Then I said quantity and quality govern, I explained. In the case of Otto cycle, quantity of air and fuel mixture which is entering into the cylinder, you can observe here there is a throttle valve. This throttle valve is controlled by driver by accelerator pedal. So, more opening of the throttle valve, more air plus fuel mixture will be entering into the cylinder, but carburetor is supplying only fixed value of air fuel ratio, around 15 it is supplying. Yes, and amount of the air fuel mixture which is entering into the cylinder, it is controlled by throttle valve. So, here quantity of mixture is controlled, that is why these engines are termed as quantity governed. In the case of diesel engine, air quantity is always constant, supply of air is constant, only diesel quantity is varying by variation of the fuel, the amount of fuel which is entering into this injector. So, if load is lesser, small amount will be entering into the injector. If load is more amount will be entering, but air remains constant, it means air fuel ratio will be varying. So, here the quality of mixture is varying. So, these type of engine, these diesel engines are quality governed, here it is quantity governed. Then here say in the case of petrol engine, only air we have taken in suction stroke, whereas in the case of diesel engine the fuel has been injected with the help of injector. In the case of petrol engine, for starting the combustion we need a spark plug, whereas in the case of diesel engine we do not have any spark plug, we are having injector, and the injector is responsible for injecting the fuel into the cylinder. The ignition temperature of diesel is significantly lower than petrol. The ignition temperature, self ignition temperature of diesel is around 180 degree, whereas self ignition temperature of petrol is 450 degrees Celsius. So, here ignition temperatures are lower, and even if no source of ignition is available, still after compression temperature of air is significantly higher. In that atmosphere, when we are injecting the diesel, combustion can be started. Pressure after compression. In the case of petrol engine, I said compression ratio is smaller. Pressure after compression, just after compression, no combustion, pressure after compression, it is around 10 bar. When compression ratio is 8, if you calculate, pressure will be coming somewhere around 9.5 10 bar. But in the case of diesel engines, compression ratios are higher. Just after compression, pressure which will be receiving, it is around 40 bar. So, diesel engines are having significantly higher pressures after compression as compared to petrol. If after compression pressure is higher, after combustion pressure still will be higher. So, in the case of diesel engines, after combustion pressures are also higher as compared to petrol engines. But temperatures, if I am comparing, in the case of petrol engines, after combustion or during combustion, the peak temperature which you are receiving, it is much more higher as compared to diesel engines. Petrol engine peak temperature is higher as compared to diesel. Reason for that one is combustion duration, up to which flame is propagating. That combustion duration, I said in the case of petrol engine it is around 40 degree of the crankshaft rotation, whereas in the case of diesel engine combustion can go up to 100 degree of crankshaft rotation. Slow combustion in the case of diesel, and in the case of petrol combustion is fast. So temperatures which we are receiving in the case of petrol engine, those are significantly higher as compared to diesels. Here heat addition processes I am indicating. Q, Otto cycle, diesel cycle, theoretical cycle, where working medium is air and heat source is outside the cylinder, that is supplying the heat to the cylinder. In the case of Otto cycle, you can observe heat addition is at constant volume, instantaneous, no time is taken for the purpose of addition of heat, whereas in the case of diesel engine, heat addition is at constant pressure. Piston is going in downward direction, inside the cylinder due to heat addition pressure should increase, but same time piston is going in downward direction, it means pressure will remain constant. So constant pressure heat addition. In the case of diesel engine, when piston is at TDC, rapidly heat has been added without consuming the time and pressure will increase rapidly. So theoretical heat addition process in Otto cycle, it is at constant volume, whereas in the case of diesel cycle, heat addition is at constant pressure. Heat rejection 2-3 here I am indicating 4-1 in diesel cycle, it is heat rejection. Heat rejection is same. Expansion compression ratios are reversible adiabatic, it is assumed. Only process of heat addition is different in Otto cycle and diesel cycle. When we are comparing both the cycles, one we are saying compression ratios are lower, and if compression ratio is lower, particularly in petrol engine, compression is easier, because for starting the engine, when we are starting the engine, we'll have to do cranking, we'll have to rotate the crankshaft with some external source. Normally we are using battery. So if compression is up to only 10 bar pressure, as I indicated in the case of petrol engines, so compression is lower, after compression pressure is less, so compressing up to that pressure it is easier. So starting of these petrol engines are easier, but in the case of diesel engine, I said after compression pressure we can receive up to 40 bar, receiving at receiving pressure 40 bar, reaching press up to pressure 40 bar with the help of external source, with the help of battery, it is quite difficult. So starting of these engines, diesel engines are difficult, but starting of petrol engines are easier. As compression ratios are less in petrol engine, peak pressures are lesser, it means the cylinder walls of the cylinder head, their thickness, the type of metal which we are using, that these weak metals, the less thicker metals we can use for the purpose of construction of cylinder head, for the purpose of construction of cylinder blocks. So weight of the engine will be smaller in the case of petrol engine, and the diesel engine pistons, cylinder head, they are to be stronger because they like to sustain very high pressure. So weight of the cylinder is much more in the case of diesel engine. The petrol engines are lighter. If it is lighter, less material has been consumed, so cost of these cylinder pistons are lesser, but running cost of petrol engine, because fuel is costlier, running cost of petrol engine is higher as compared to diesel engine. Maintenance cost, because pressures are lesser inside the cylinder in petrol engines, less vibrations will be there, less wear tear will be there, so maintenance will be lesser here. Thermal efficiency, because lower compression ratios are there, the thermal efficiency of these engines are lesser, say around 26-27% we are having. Here overheating problem will be there. I said peak temperatures in the case of petrol engine, because combustion is faster, peak temperatures are more. If peak temperatures are more, then overheating troubles are there. Even lubricating oil, the life of the lubricating oil which we are supplying to the cylinder for the purpose of lubrication, that life becomes lesser because they let to sustain very high temperature. Their lubricating oil lubricating properties will be destroyed due to the high temperature. Petrol engines are high speed engines. I have given the example, even engine is running at 6500 rpm, even engines are running at 10,000 rpm. So speed of these engines are quite high. Normally they are used in light duty vehicles, scooters, motorcycles, car. The diesel engines are for heavier vehicles, in the case of trucks, military vehicles, marine application. In the case of diesel, I said compression, after compression pressure is quite high, 35 bar, even 40 bar. Just after compression, and the fuel is injected in the form of fine sprays, separately air is taken, fuel is injected into the cylinder. After compression, even temperature may become 600 degrees Celsius. After combustion, in diesel engines temperatures are 1500 1600 degrees Celsius, but in petrol engine, after combustion, during combustion, peak temperature may become 2000 degrees Celsius. So after compression, here temperature is higher, but during combustion, in the case of petrol engine, temperatures are higher. Combustion of fuel, in the case of diesel, it is at constant pressure, roughly I have shown you. In the case of Otto cycle, it is at constant volume. Compression ratio is ranging from 15 to 25. High compression ratio in diesels we are observing. Here starting is difficult because compression ratios are more. We will have to compress up to the high pressure by external source. So starting of these engines are difficult, and these diesel engines are heavier because they have to sustain high pressures inside the cylinder. The weight of engine will be much more. If weight is more, the cost of the engine will be higher, but running cost here will be lesser because cost of the diesel is less. Here maintenance cost will be more. They will have to sustain high pressures, high temperatures. So the frequent maintenance, frequent changes in the cleaning, everything will have to do in the cylinder. Again and again we will have to see the components of the engine, because they are passing through a very high pressures in the cylinder. Here due to higher compression ratio, thermal efficiencies are higher. In the case of petrol engines, I said it is 26-27%. Here conversion efficiency is around 30%. Physical meaning of this one is that whatever heat we have supplied to the cylinder, out of that around 30% has been converted into useful power output. Here overheating intervals will be lesser because peak temperatures are less. Only 1500 degrees Celsius peak temperature we are achieving here, and the speed of these engines are lesser, around 4000 rpm, 4500, that will be the maximum rpm, whereas in the case of diesel engine it can be up to 10,000. And these are used in buses, trucks, earth moving machines, marine applications, I said diesel. So some of the conclusions here: in the case of petrol engine, a homogeneous mixture of air and petrol is applied. In the case of diesel, only air is applied. The compression in the case of petrol engine, it is ranging from 8 to 12, whereas in the case of diesel engine it is ranging from 14 to 25. The air fuel mixture is burnt with the help of spark plug in petrol engines, whereas in the case of diesel engine, fuel is injected where air temperatures are significantly higher. In that atmosphere, diesel is injected. So without the use of spark plug, combustion can be started. Petrol engines are lighter in construction because pressures are lower. Petrol engines need less maintenance also. And diesel engines are more efficient, I said, because their compression ratios are higher. Their power output is, petrol engine gives more power as compared to diesel engines, but fuel is costly. More power they are giving with same size because combustion is very rapid. Very rapidly they are giving the power. So their power output from given size engine, in the case of petrol engine, is much more as compared to this one. Petrol engine can destroy lubrication, I said, because temperatures are higher, lubricating oil can burn in cylinder itself. Petrol engines are lighter, and these diesel engines can pull very heavy loads up to a longer distances they can carry. The diesel engines would be steady and heavier, yes, heavier, because their pressures, peak pressures are higher. Diesel engines have better efficiency. Reason for that one is their compression ratios are higher. Diesel engines are giving better mileages, means higher efficiency means better mileage also. And diesel engine is much cheaper than petrol. Only fuel part I am saying, I am not saying engine part. Diesel engine will be costlier as compared to petrol, but fuel is cheaper. Diesel fuel is cheaper as compared to petrol. And no ignition system, separate ignition system is needed in the case of diesel engine, whereas in the case of petrol engine we are having spark plug, we are having ignition coil, we are having capacitors, we are having separate battery, we are having ignition switch, everything will have to have. So cost wise, if you are comparing, petrol engines become more costlier because many additional components will have to add for starting the combustion. In the case of diesel engine, the combustion is just after compression, it is very easy also. Then in the case of diesel engine, for starting combustion, particularly when temperatures are low, at low temperature, when we are starting the engine, particularly early in the morning when we are starting, when temperatures are lower, starting becomes difficult. That time, for heating the air inside the cylinder, some heaters or glow plugs are needed, which is heating the air, and on glow plug or into the high temperature air we are injecting the diesel. So for starting purposes, some of the diesel engines are having glow plugs, but these type of glow plugs are not needed in the petrol engine. With this I conclude, and what we have studied here today, the differences between the Otto cycle and diesel cycle. Otto cycle, we said they are adding heat at constant volume. We said in the case of diesel cycle, heat addition is at constant pressure. The peak pressures in the diesel engines are higher as compared to petrol engines. Diesel engines runs at lower speed as compared to petrol engines. The combustion duration in the case of petrol engine is lower, around 40 degree of the crankshaft rotation, whereas in the case of diesel engine it can be around 100 degree of the crankshaft rotation. And the weight of the engine, in the case of diesel engines, weight is more as compared to petrol engine. Next time we'll be discussing like volumetric efficiency, how power output from a given size engine can be increased, what is mechanical efficiency, what is the indicated thermal power efficiency, what is brake mean effective pressure. So those parameters of the engines will be discussing. Thank you.